So, before I say anything else, I want to say thank you. I mean, I've traveled around the world to be here, and well, here you all are. Like, look at all these people in this room, all the speakers who came here to try and make everybody better, and all of you who showed up to try and get better. Wow. Like, I keep going different places in the world, and people show up and do that. I'm genuinely honored to be here. In return, I will try hard not to waste your time, because you've all brought a lot of time here, and I'll do everything I can to do well by you. So who am I? I work on YJIT. I work at Shopify. If you go to speed.yjit.org, you can see lots of little wiggly graphs about how fast it is or isn't, and that was a lot of that was me. I wrote a book called Rebuilding Rails. Some of you have said very nice things about it. Thank you. I appreciate that. I'm writing a book called Rebuilding HTTP. Same general idea, learn HTTP by building one. But more importantly than any of that, I'm the guy with the bear. Ask me for bear stickers. There was a stack out there. I'll put another, well, I don't know if I'll put another stack out there, but I've got them. Ask me. I'll gift you bear stickers. So this will shock everybody who's been listening to me for the last few seconds. I tend to talk fast. So if anybody thinks that maybe the person next to you can't take quite my full speed, if you were to yell out, slow down, I would appreciate it. It would be a favor to me. I love questions. This topic is a little bit complicated. If you have a question, somebody else in this room pretty certainly does too, please ask it. I'd love to answer it. The worst that happens is I'll say, I'm not answering that. You say, what's your ATM PIN number? I'm going to say, I'm not answering that today. Or wait for another slide. But there's no Q&A at this conference, so if you don't ask before the end, you've got to grab me later. So if you yell it out now, everybody gets to hear. There's also a, not answering that today, but good question. I appreciate it. There will be a resource URL toward the end of the talk, so when I put up little snippets of code or little URLs, you do not have to type them feverishly. You're going to get one chance to type the URL at the end, and you get all of them at a go in your web browser. I don't give the resource URL at the beginning, because I'd rather you pay attention and ask me questions. So, okay, multiple representations all at once. It sort of sounds complicated, but no, really, why do we care? Why is this worth 40 minutes of your time that you could be using for anything else? Well, a lot of software development work is about keeping multiple representations in your head at once. And we're going to talk in a lot more detail about what I mean by that, because I'm going to give you a very specific example of that. But a lot of what you do is keeping multiple things in your head at once and working with them together. And I think YJIT is a really good teaching example of that. It also happens to be what I work on, and I think at least some of you probably care about YJIT because it'll make your Ruby faster. But it's also a really good example of this. Cool. And YJIT does a lot of translating between representations, which is another fantastic way to learn stuff. Those of you who work on interpreters and compilers in here, you know what I mean already. So what's YJIT? I keep saying YJIT. I haven't actually explained what it is. So it's a just-in-time compiler. It's built into CRuby. It's been built into CRuby for just almost a year now. In 2 weeks, it'll be a year. We've been working on it longer than that, of course. And it makes your frequently used code fast by compiling a method after it's been hit enough times, and it waits for a while to compile it. You might say, why not just compile everything right at the beginning? I've heard languages can do that. No, it waits as long as possible to compile your code so that it knows as much as possible about the actual values and types going into the code. And it turns out we get some good optimizations that way. When I say CRuby, if folks don't hear that very often, that's the same thing as Matz's Ruby. It's the same thing as just plain Ruby or vanilla Ruby. But when I say CRuby, I mean that Ruby. I do not mean JRuby, Rubinius. Those are not CRuby. Cool. And you might say, wait, hasn't Ruby had a JIT longer than that? MJIT is the older JIT. It's still in there. You can use either one. Like the 3.1 has both, 3.2 is going to have both. But at this point, MJIT is more sort of experimental, and Kokubun-san's getting to actually play around with it more. He's so happy. He works on both. I don't know when that man sleeps. But both JITs are in there. But YJIT is now the favored JIT for speed reasons. We'll see. Maybe Kokubun-san will come up with the third CRuby JIT and blow us all away. That would be fantastic, because one thing we can always use more of is performance. Okay, but so YJIT, it's a JIT. So how's it work? When you start up your Ruby process, nothing is compiled. You know, you've got the interpreter, nothing's already compiled. After The default in the new one is 30 calls. It's a command line parameter. You can change it. But after a certain number of calls, YJIT goes, oh, okay, you're probably going to call this a bunch more times. Let's compile it. And so it's going to turn your Ruby code into native machine code. And again, it waits as long as possible to do that. And when I say it waits as long as possible to do that, it'll cheerfully go through your method, and as it compiles it, it'll run a little bit and then compile the next bit, run that next bit, then compile the bit after that, so that it knows the types and values of all the things that it's dealing with on that 30th call. So it swaps back and forth a lot. It's not concurrent, you know. Those of you who work on, say, JRuby may be thinking, does it use a background thread? Nope. It's the same process, switching back and forth repeatedly. Yes. So I keep saying it swaps back and forth. Is it just for compiling? No. So there are some cases where the interpreter handles a case we don't handle at compile time. Like YJIT tries to hit the most common things where we care the most about speed and can do the most good. And so there are a lot of operations where it's slow or it's weird or it's not frequently used and we just don't handle it. Like if we hit that, we go, okay, this is not our method. Interpreter can handle this method. There are other cases where we think we can handle it and then it's Ruby. You can change everything, you know, whenever you want. And so sometimes it throws us a change up. You know, sometimes you've been passing an integer into this method over and over and you decide to change your mind and now you're passing a class in where that integer used to be and we go, oh, well, that's not what we compiled. Right, side exit, interpreter, take over. And sometimes assumptions just break. You know, you've been using time.now repeatedly and we go, oh, we know a really fast way to call time.now without the full Ruby call. And you say, oh, by the way, here's what time.now is now defined as. I'm going to monkey patch it. Oh, oops. Okay, and so we take all those things where we compiled time.now and we wipe the slate clean on those. And once we've hit it 30 more times, then we're going to compile it again with your new definition of time.now. So we switch back and forth with the interpreter a lot. Cool. That probably sounded like a little YJIT theory, but I work on this all day. I could talk about it all day. Don't worry, I won't. But YJIT is based on what's called lazy basic block versioning. We'll talk more about how that actually works, but it's based on a research paper by Maxime Chevalier-Boisvert. She's these days my tech lead. She and a fellow named Alan Wu built the original prototype of YJIT, which became the YJIT team, which is now what I work on and where I work on it. But the eCoop 2015 paper, it's linked from that resource URL I'm going to give you, describes in a lot of detail if you'd like to read a formal researchy white paper. And if not, you know, don't worry, we're building it for you. But the idea is that YJIT takes a method, it divides it up into these basic blocks, little chunks of functionality, and then it compiles those into machine code. It's not a Ruby-specific idea. Her first implementation was JavaScript. She went to work for Shopify, looked at Ruby, and sort of went, oh, I know a way we could make this faster. And Shopify said, great, go do it. Cool. So YJIT compiles an iseq. Usually that's a method. There are a few other things like blocks that are instruction sequences. So Ruby calls them iseqs, but YJIT compiles usually a method, splits it up into basic blocks, compiles the basic blocks. Well, those are split into bytecodes and it compiles the bytecodes. You can see the details of how it does all this if you've got a development build of YJIT. If you wonder, how do I get one of those? It's in the resource URL. I promise you'll get it. But you can use this little snippet of code and it'll cheerfully dump all of the assembly language instructions. It'll cheerfully dump all of the division into basic blocks. It'll show you all of the details of what it turns into. So if you're the sort of person who wants to debug your assembly language, I know most of you aren't, I get it. But if you are, we would be thrilled to show you what we've been working on all this time. You just ask for it. We'll dump more on your console than you'll read anytime soon. It's great. Great, but again, this only works on dev builds of YJIT. If you do it on a regular build, all you will get is the Ruby bytecodes, which we'll see in a few slides. So now that you know a little more about what YJIT is doing, now I can tell you about that multiple representations thing and why I think you should care. I know I keep coming back to why you should care, but again, this is all about why I think I'm not wasting your 40 minutes. So as a software developer, you probably juggle a lot of languages. I mean, as a Rails developer, you probably juggle a lot of languages, but those of you who are not Rails developers probably still juggle a lot of languages, because you got your programming language, you've got your domain language, which is not quite a programming language, but it's a similar set of steps and things that you have to spell out. Your app does things in a particular way, and the longer it goes and the bigger it gets, the more you've got a whole little language of your app. APIs are like their own little language, and yes, somebody else has usually developed them, but you get to translate to them. You're juggling languages all the time. You're doing this constantly. And as a good developer, and the longer you do it, the better you get at this because you have to practice all day, the more juggling languages is a lot of what you do. I have a feeling a lot of people in this room are really good at that, and I don't just mean the ones that I know work on interpreters and compilers. So that's cool, but if we all do it every day, why is YJIT an interesting example? Well, compilers spell out exactly what their languages are really specifically. Compilers are all about, very specifically, hey, we've got a Ruby bytecode language. What is it? Let's start the documentation. Oh, hey, we've got, this assembly language thing. It's clearly a different language. It's documented that way, so it's clear what the steps are. And if I'm going to explain things, concrete always beats abstract. Giving you an example that does something always beats abstract every time. And YJIT is an interesting mix, because putting these languages together is where a lot of the power comes from the combination of it. So, okay, Ruby bytecode. Ruby bytecode happens with or without YJIT. Your Ruby is doing this anyway. YJIT messes with it, but bytecode is just how Ruby operates. Ruby turns your code to bytecode. The Ruby bytecode is a stack machine. Anybody remember Paulo's talk where he was talking about forth? Ruby internally works like that. You push the arguments onto the stack, and then a bytecode thing is going to pop those arguments and push its return value onto the stack. Do people remember forth? Yes? No? I'm seeing a noticeable bit of yes. Cool. And again, all this is true whether you use YJIT or not. This is just how Ruby internally works. So you can get Ruby to give you a bytecode disassembly. I showed you the YJIT disassembly earlier, but Ruby will cheerfully give you a bytecode disassembly. We're not the only ones that like to brag about our work. This snippet is also in the resource URL, so again, you don't have to be carefully writing it down. But we're going to do that. We're going to take this very simple little method that does a putS, and then if the single input parameter is true, it does another putS. And we're going to see what that turns into in Ruby bytecodes. I'm so sorry. No, that's the code on the right. And then if you can see the highlighted column there, that's the list of bytecodes that this fairly simple Ruby method turns into. So put self, put string, opsend without block, pop. If you can see better than I can, like if your eyes are better and younger than mine, you can even see some of the other data in there, like the string yes. It's just, in gray instead of black. But those are those stack machine bytecodes. Put self means take the current self, push it onto Ruby's internal stack. Put string, in this case put string yes, means take that string, push it onto Ruby's internal stack. Opsend without block pops off that receiver, pops off that string. It's opsend without block of puts, so it calls put on those two things. And so again, it's like forth. Pop off the arguments, call it, put the result back. This one doesn't even use the result, so there's a pop right after to get rid of the thing that we pushed onto the stack. Fair enough. Stack machines do that. And the branch unless, I promise this is the last bytecode I'm going to explain from this one. The branch unless just means if a thing is not true, then jump. And in this case, that's because we've got that if in there, and that's how we get to the end of the method and do nothing if the condition is false. Cool. So when YJIT compiles the bytecode, it just does them one by one, one after the other. Each bytecode turns into a chunk of machine code. The chunks are mostly consecutive, because if you have a chunk of machine language code for somewhat complicated reasons, you just want it to be a simple straight line straight through as much as you possibly can. And so that's how we compile it, as much as we possibly can. If all this bytecode stuff has made you think, oh, I need more of that, like I could have 3 hours of talk just on that, you are having such a good day today, because Kevin Newton is in the middle of writing a long series in great detail about this. It's linked there, but it's also in the resource URL. So this is a similar but different method. It's a little more compact, but it does a method call. If the condition is true, it does another method call. And now you can see the set of basic blocks that all those bytecodes turn into. It probably looks like a lot of basic blocks for a method this size. I know it does to me. We're working on reducing the number slightly, but it turns out this works surprisingly well. A lot of small basic blocks works out fine. But this is what it actually does. And you could reasonably say, I'm not going to work on this code. Why do you keep showing me all the little bits of this code? And that goes right back to concrete examples work better than abstract examples. I want you to see a little bit of what it actually looks like so that you can tell it's a real thing. Anything too clean, my eyes just glaze over it because I know that whoever it is lying to me. This is this dirty because it's the real thing. If you're really quick on the uptake, you may have noticed that the assembly on the right doesn't have 7 little boxes like the bytecodes. It has 2 little boxes. And that is because You generate a lot of assembly. That first little box is, in fact, the complete output for put_self, because put_self is this tiny little simple thing. And that second box is like somewhere between 1/4 and 1/10 of the output for upsend without block, because, now you know, Ruby method calls are large and expensive. If you ever wonder why, man, have I got the computer program to show you just exactly how that works. We've got a little disassembly for it built in. But no, YJIT can show you in great detail what Ruby actually does for a lot of this. Okay, so that was a significant amount of sort of dive into what Ruby does and how we translate it. What does YJIT actually, use for this? I sort of waved my hands and magically basic blocks turn into assembly, but obviously there's something more to that process. And so we're going to talk about an additional language, that's YJIT's context structure and its intermediate representation. Don't worry, I'll tell you what those are. But here I say one language, and then I say a context and intermediate representation, one language. That's on purpose, and that's because languages are this kind of squishy human concept. We would love as programmers to believe that a language is the set of input strings that a particular tool accepts. Doesn't that sound comforting? That sounds really detached and comforting, doesn't it? It's a complete lie. It's utterly false. Because when you talk about a language, you're talking about recommendations for how you use things, you're talking about how you make sure the next person can see it and understand it. So anytime somebody says a language, Ruby is used in what, 15 or 20 different ways in different contexts off the top of my head. Like when you're writing a controller, you don't write it the way you write your rake file, you don't write it the way you do the next thing, and you get different recommendations for all of those. Ruby is not one language, Ruby is 20 languages. And when you get recommendations for Rails, you don't get recommendations for Ruby code in Rails. You get recommendations for, like, it's Ruby code and it's SQL and it's the asset pipeline, and oh, we should probably, put Urban Haml in there because they're both used, and what about, Minitest and RSpec, which are very different things from each other. Because a language is a human squishy concept. If you're thinking about translating between languages, you're constantly thinking about turning from one thing that is meant to communicate mostly with other humans, and the computer happens to execute, to another thing that is meant mostly for humans, and the computer happens to execute. So, since what I'm hoping you come through this, I know a lot of you are feeling shell-shocked already, what I'm hoping happens as we go through this is that you come away with a little more of the understanding that what we do is all languages meant for humans. At some level. The computer happens to execute it, and that's nice of it. We appreciate that. But it's not what it's for. Okay, so BBV, again, that's basic block versioning. It's how YJIT works. BBV and context. So YJIT remembers a bunch of types for things. I'd mentioned that you get a lot of performance by remembering the types of things. A context is the object that holds that. It remembers for each object, was it nil, was it true, was it false, was it a string, is it on the heap or not? It's got an enum. It remembers some things about it, and it's got a fixed list of things it can remember about any given type. Different basic blocks have different contexts, which should make sense. They look at different data, so they got a different set of things they pay attention to. And in some source code, you've got a case where the same variable can have more than one type. It's perfectly okay to have a plus thing that you can put an integer or a floating point number into, and it turns out we have to care at that level, and so it gets two different blocks with two different contexts, because it turns out those generate different assembly. Okay, cool. What's it look like? That's the question I hope you sort of knee-jerk respond to when somebody says this, is to stop and say, yeah, but what would that look like? Here's what this looks like. Here's what a context looks like. You can say, let val type equal context.getOperand type instruction operand. It's a little bit, wordy, but what it means is I've got this operand. Tell me everything you know about the type of it. And sometimes the context will say, I don't know anything about that, unknown. And sometimes it'll say, I know it's on the heap. And sometimes it'll say, I know it's a string. And it'll pass back one of those things. And you can do the same thing. You can pass it, stack operand 0. If you don't have one of those operands, you can make one. And you can say, what do you know about the type of that thing that's at the top of the Ruby stack? I care about that because I'm about to pop it and do something with an operand. Or you can say, I've just found out more about the type of this object. That's what the context.upgrade operand type does, is you're saying, oh, by the way, I'm about to say that this has to be a string, so you should remember it's a string, just in case I want to do something with it later. Next time I ask you, it's a string. But that's what this looks like. Kind of like a hash table in concept, isn't it? But that's what this looks like. And then this one I'll really skim by quick, because how many of you really want to spend your time on assembly? But we tell it about the assembly so that YJIT can generate the assembly. And this is a very assembly set of things. You declare, I've got this register, here's the offset from it. by the way, go ahead and do a bitwise AND of that thing and set a flag, which is a very assembly set of things to do. But basically, we keep it just portable enough that we can turn it into Intel assembly or ARM assembly or whatever. So what ARM directly touches has to be, or what YJIT directly touches has to be a little bit above that assembly that you saw so that we can translate between multiple processors. Cool. Well, you've been listening very patiently, and what I haven't really done is I haven't brought these things together. I said I was going to explain some languages, and I was going to bring them together and tell you why it was interesting that more than one of these happened, why it was interesting that more than one came together. But I did threaten you with a concrete example, and we've gotten to some of that, kinda. You've gotten to look at some of this, but we haven't had a concrete example yet. So let's do something interesting. Let's have a concrete example, and let's talk about why it's interesting that multiple of these languages come together. The code is a slightly simplified version of an actual chunk of YJIT. I think it's current as of last month, but it's real code. If you were to put back this code from last month, it would work just fine this month. We've just optimized it slightly more, and so we have a more complicated version now. But this is working code. So let's look a little bit at that. This is Rust code. Some of you have already recognized it, some of you haven't, and an awful lot of you don't care and don't have to care mostly. It's a language with types attached, and frankly, that's enough for you to know here. If you decide you care later, I'm going to tell you where to find lots more of this. And if you decide you don't care, well, it's a language with types attached. Like you've used a bunch of languages. It turns out you can read this mostly. So we have a function called JIT RB stirconcat. If that sounds like it concatenates a string, yep. This is the shuffle operator, the less than operator. I don't know how many of you heard it called the shovel operator, but it's a string concatenation operator. It takes one string and it puts it into the other string. It's used pretty often, and it's a great example of the kind of little method where if YJIT can speed it up a lot, it can speed it up by a really high percentage, because it's the kind of thing where the basic idea is really fast, and going through a full interpreter Ruby method call is slow. So you can get a lot out of this. So this is YJIT's implementation of using the built-in string concat. So it's got a bunch of complicated looking things there. Let's talk a little about what they are. So it passes in a JIT state. JIT state is what block are we compiling? What instruction of that block are we compiling? It's basically where are we? When I went through that, you got a method and it's divided up into blocks and that's divided up into bytecodes. Like this is where it sort of puts its finger on that diagram and it says, here, we're here on that diagram. So that's what the JIT state is. It's got a context. The context, again, is that thing we saw how it works, where it acts like a bag of types. You tell it, I've got this thing, and it says, great, here's what I know about the type of that thing. We've got an assembler that's to make the output. That's the thing that's going to take a list of instructions and turn them into a big chunk of machine code for you. And so when you saw, this is how we make machine code, using the assembly code. That's the object that we use for that. And it's got an outlined code block. I haven't been talking about this one because it's a little bit of a special case, but I did say we're trying to write everything out in a line, one thing after another. And that means that any code that isn't going to be hit most of the time, we want to put somewhere else. Where else? Well, the outlined code block. Turns out that doesn't all have to be together because that's reserved for cases where we say, oops, okay, done now, interpreter, take over. And so we want to get all of that out of the regular flow of control so that when everything goes well, it just hits the good case and the good case and the good case. That's where we put the bad case. The slow case. It's not the bad case. It's the slow case. And then in this case, we've got several parameters that luckily we don't use here. If you stick an underscore in front of them, then Rust will say, you're probably not using that. And Ruby actually, a lot of folks use the same convention. But we have the ability to compile more complicated things. And again, I'm mercifully giving you folks a slightly simpler method. We have some more complicated ones. But you can not worry about the things with the underscore because this method doesn't and says so. All right. So this is the start of the method. I say you switch back and forth all the time. That JIT peek at stack, that's the first switch back and forth. That's basically saying, if you're in the middle of compiling this, wait until we're actually going to run it, because I want to see what the runtime object on that 30th call actually is. Like, grab it out of the C Ruby and show me what it actually is. So if we're not there yet, wait until we're there. So that's what it's doing. And then once we can grab it, we do, and we say, check at runtime. Is that a string? That's a string, right? Is that a string? Because if it isn't, we're going to say, oh, we can't compile this. If you pass in a struct, well, you're going to get an error, but also we don't want to give that error. We let the interpreter give that error. If you pass in an integer, it turns out that, like so many things in Ruby, string concat will do a bunch of different things depending on what type you pass in. And if you pass in the number 65, it turns out it's going to add an A. Those of you who already know ASCII are nodding your heads, and everybody else is going, what? But if you pass in an integer, it'll cheerfully decide that you mean a code point, and just like you don't really want to mess with that, neither did we. We kicked that back to the interpreter. That's not a case that people use much, and it's not a case we cared about being fast, so mercifully, we can kick back to the interpreter until one of you writes a program that really depends on that, and we get it as a test case, and then we get to fix it. But for now, we kick out and we don't fix it. So okay, and in that case, we return false. We say, you know what, we can't compile this. So that's one of those ways to switch back and forth. And then we generate the side exit. We only generate the code for the, for the difficult case if we think we're going to need it. So if we just kick out and we don't do anything, great. We don't have to generate a side exit. We can save a little space. But we generate the side exit, and then we say, hey, we're about to pop this thing off the internal stack. Tell me everything you know about the type for it. So this is, again, a compile time operation. And it's something that doesn't necessarily assume it knows the runtime stuff. It's probably a little bit dizzying. I know it was for me. I work on this code all day, and it's a little bit dizzying for me to go back and forth between, oh, this is what it knows at runtime, and this is what it knows at compile time, and I go back and forth. But the reason you care about compile time is that there's going to be a bunch of checking all this stuff. Like, we've already started with all the checking stuff, and I promise you there's more, even in the simple example. And by far the fastest way to get through this is to do nothing. This is going to let us do nothing by mixing that compile time and that runtime. It's dizzying for the same reason it's powerful. Because if you can sit and actually think through these languages, it turns out you can often get to cheat. And cheating, doing nothing, is often by far the fastest thing your program can possibly do. And I'll tell you exactly what I mean by cheating and doing nothing in one more slide. But we get the argument type, and then we pop those arguments off the stack, because we're about to use them. Here's where we get to do that cheat. We take that compile time argument type that we said. We said, what do you know for sure at compile time about this object? It has to be what? And if it doesn't know anything, it'll say it doesn't know. But here we say, if you know it's a string, and in this case it means string or string subclass. That's what C string and T string are. But we say, if you know it's a string, you know what? Don't do anything. Just skip this whole block. That'd be great. If we don't know it's a string, then we say, well, do you know it's on the heap? If you do know it's on the heap, you skip half of this block. And if you don't know anything about it, then we're going to have to say, is it on the heap? Because otherwise, if we try and touch it like the wrong type of object, this is assembly language and it'll crash. We're back in the land of segfaults here. But so we check, and we check whether it's on the heap, we check whether it's a string. And this isn't a giant amount of code, but it's a significant amount of code, and we'd love to skip it. And so by having this compile time representation, where we do this and then we say, oh, by the way, now we've checked and it's a string, that means if you were to say concatenate, 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 if you build your string by doing add a string, add a string, add a string, add a string, that first one it's going to check like this. And every one after it, it's going to say, oh, by the way, I checked at compile time. This thing's a string. And it will skip all of these checks and just do the simplest, fastest thing to add every time. And that's a lot of why YJIT can be faster than the interpreter. I mean, they're kind of doing the same thing. In fact, if we're doing our job right, they're doing exactly the same thing. But we can cheat and do nothing in a lot of cases because we verified it, we took notes that we verified it. What does that mean? Well, it means that context thing. It means exactly what you looked at, where we say, oh, hey, this is a string, and next time we ask, it'll say, oh, hey, this is a string. Which is in some ways not magic, because you stick the thing in and you get it back out and it's the same thing. And in most ways feels like magic, because isn't it awesome to get to, do the same thing faster randomly? Not randomly, you know what I mean. It's always magic when the program works. But that's really the magic. That's where that comes together, where the compile time language and the runtime language do something really interesting when they come together. And from there we get to the pedestrian work. I promise this is the last slide of this function. From there we get to the pedestrian work of actually doing the thing. I simplified it so that we didn't have another slide after this. And this is where we just call down to the thing that actually concatenates the two strings. The real version checks the string encoding, but string encodings are not something I wanted to explain to you in this amount of time. The real thing checks the string encoding and can go to an even faster thing if it can verify that they're basically the same string encoding and just smash them together. This is the next best thing. But that next best thing is, again, the stack machine. We've got these arguments, we've looked at these arguments, we've guarded these arguments, or better yet, we haven't, and now call the method and just put it right back on the stack. And that's what you're looking at there. And I said there was the magic where you could say, we know it's a string. Sure, okay, there's the thing that you checked was a string, but you also need to make sure you're putting a string back. And so here we are saying, we happen to know this string concat will always give us a string. Yes, it's a string. And so when we push it into the context, we push it as a string. Because for this one, we know what it is. In Ruby, you almost never do. For this one, we do. Probably feeling like a lot. So yeah, now you've seen a lot of code. Why do you care? So it's a bit clever, and it's a bit tricky. Those are the worst things about it. Tricky and clever, those are the worst things about that code. We try really hard to make it simple. I promise you, to my shame, we work really hard to simplify it, and this is how far we've gotten. To some extent, tying those three things together is just hard. The interesting thing is not that it's clever or tricky. The interesting thing is by sitting and working through, on paper a lot of the time, here it's this, what is it at runtime, what is it at compile time? By weaving those things together, you can get something that's way more powerful than the things that are there separately. And so when I say, as you become a more and more senior developer and you get good at this, notice I didn't say, look how easy it is for people like me. Like Maxime is ridiculously smart. I'm no slouch myself. Alan is ridiculously smart, and we sit and we ploddingly work this out on paper. But the result is incredible just because we've practiced it and learned about weaving those languages together. And so as I explain it to you, and I say to my shame, it's still this complicated because, you know, I said a language is for explaining to people. You are getting to see where we screwed up, where we failed in trying to make this comprehensible to all of you. I'm having to explain it very slowly and carefully in the same way we work through it painfully. And I mention the shame over and over again because this is something where we're not compromising on the power. All of you get a really fast YJIT, all of you get a really fast Ruby. And even when we've been doing this a long time, I mean, pretend I'm an idiot for a moment and just assume that you know, Maxime and Alan aren't idiots. Very smart people, them at least, whatever whatever I may actually be like, you don't know, you haven't coded with me. But very smart people work through this, and we're trying really hard to make it comprehensible. And the right thing to do, the thing that would serve all of you best, the thing we should do and we know we should do and we work hard to do, is to make this comprehensible to people. Because you could say, we've got something really clever, we've got something that works, the machine executes it, that's enough, right? And the answer, of course, is no. No, it's not enough. Because we would love for all of you to be able to sit down at this and say, oh, I see what it's doing. By the way, you've got this thing it could do better. And right now, that's hard. Right now, we are not serving you as well as we should serve you. Right now, you know, looking through this requires an expert to slowly walk you through it badly. Which runs the risk of sounding like, you know, don't be like me, here I am, you know, Marley in the story of the Christmas Carol and Scrooge. Like, no, but understand that as you get better at this, you're not getting better at talking to the computer. This is a room full of people who are fantastic at talking to the computer. And yay, that took a ton of work. Go all of you. But someday I will be so good that I can do this in a way I can explain well to people. And I hope all of you can as well. All right, so you've made it through a ton of this. I know it's warm in here. I know this is a hard topic to follow. Again, thank you, all of you. You know a lot more about YJIT now. You know more about how it does what it does, and a lot of you could now read through the code and get something interesting out of it. This code is all just right out there in the open, and some of it you've now already read. But you can see more of how it does what it does. And I'll talk a little bit about where YJIT's at, because again, this is a thing you can use even if you don't ever want to look at the code. Most of you will never want to look at the code, and I'm cool with that. But many of you will want to use YJIT. So it's pretty fast. It's pretty robust. We have trouble crashing it, and I promise I try all day. That's a lot of what my job is. You know, I do a lot of benchmarking and weird cases. I try to crash it all the time. You can see latest speed results on cute little wiggly graphs, and you can get, you know, in-depth current results and how it's been changing over time at speed.yjit.org. That's mostly me. So if you see a problem with it, I'm the guy. Feel free to make a bug report. It's best for long-running code. It's a JIT. JITs are best for long-running code. So if you're running something like bundle or gem just from the command line, the JIT is not going to do you much good, and that's okay. The reason that we've moved the threshold up to 30 is so that we don't screw that up. Because JIT's good for something like a Rails server that sits and runs for, you know, seconds or minutes or hours rather than quarter of a second. We'd call it limited production ready. The memory usage is a lot better than it was a year ago. We've got it garbage collecting generated code so that it won't run out of memory eventually if you run it long enough. Just in general, it's in good shape. It supports both x86 and ARM. So if you have one of these lovely fancy new Mac laptops, this one's just an Intel, but if you have one of the lovely fancy Mac laptops, it'll cheerfully generate native code for you there. So it'll run nice and fast. Yeah, the new release that comes out on Christmas is the one that is the lower memory usage that supports ARM. Most of the good stuff I'm saying comes out in 2 weeks rather than right now, but it'll come out with the rest of Ruby. And if you go to the resource URL, which is coming up in the next slide, it'll tell you about how to use it. But the short version is you add --YJIT to the command line. Also, if you use YJIT in production, we'd love to hear about it. Like, we want to know. We have some internal use cases, and we have a few people who've used it and told us about it, but if you're using YJIT in production, man, tell us. We want to know. There you go. YJIT's in the CRuby source code. There's the link to the lazy BBV white paper. And I keep saying this, you know, this thing's at the resource URL, this thing's at the resource URL. It's, you know, there's a fair bit of stuff there, but that's the URL. If you were going to write something down to look at later, that would be the one. And I'll also send it out to the Slack for the conference.